Doing some exam questions or exam style questions on the particle physics part of the AQA specifications for A-level physics. Okay, let's get stuck in. So, question one. So, they're going to be, first of all, going to be a combination of multiple choice questions and long-worded or non-multiple choice questions. So let's get started. So we start off with some multiple choice questions. We've got to tick which is the right box, which row. So it says which row in the table correctly describes a francium nucleus. So 215 is the mass number and 87 is the atomic number. Well, in terms of hadrons and baryons, remember baryons were protons and neutrons. They were made up of 3 quarks. If you watch the video where I go through the theory, you would have found out that protons and neutrons are made up of up and down quarks, and hadrons are split into 2 categories, mesons and baryons, and the mesons were made up of a normal quark and an antiquark, and they came in these pairs. But in this particular case, the correct answer is going to be B, because we don't have any leptons, because it's just a nucleus. If it was an atom, then it would have potentially, well, we could consider A and C, so it's only going to be B or D. But because we know 87 is far too small of a number because it doesn't include the neutrons, and neutrons are also baryons. So the correct answer is B. Okay. Right, let's look at question 2, the neutral lambda baryon. So this is actually an example of a heavy baryon. I didn't go through it in my lesson on particle physics, but a heavier version of protons or neutrons, where a heavier baryon is the one in front of us, a lambda neutral baryon. And it tells us the composition is a U and a D and an S. And remember, I said the S quark has got the property of strangeness, so it's got a strangeness of -1. Now, we need to go through all the conservation laws to get this answer. So I'm going to actually do process of elimination just to show you and to also give you some practice of these conservation laws. So we've got a baryon number of 1 on the left here, baryon number of 1 for the proton, baryon number of 0 for the negative pion, because remember it's a normal quark and an antiquark, and that's a plus 1/3 and a minus 1/3 in terms of the baryon numbers, so they cancel out. And the baryon number of the E is obviously 0 is 0 because they're leptons. So baryon number is conserved. Let's look at lepton number. Lepton number is +1, -1, 0 on the left. These guys are 0, so lepton number is conserved. But let's look at charge. So we have +1, -1, -1, 0. So we have 2 minus, a sum of 2 minus on the right, and a charge of 0 on the left. So charge is not conserved. Okay, so D is incorrect. Let's look at B. Charge of 0 on the left, charge of +1 on the right. Already charge is not conserved. Baryon number is conserved because this is 0 and 1, 1, and the lepton number is 0, 0. So the charge is not conserved. So B is incorrect. Let's look at C. We have, let's start with charge. So we have 0 on the left, then we have +1, -1, which is 0, and then that's 0 for the electron neutrino. So charge is conserved because the plus and the -1 cancel out on the right. So it's 0, 0. Let's look at baryon number. We have +1 on the left, +1 on the right, 0, 0. Baryon number is conserved. Let's look at lepton number. Lepton number is 0 on the left, 0 for the proton, +1 there, but this is an electron neutrino, so it's also +1, so lepton number is not conserved. And then if we look at A, obviously process of elimination, it's got to be correct, but let's just go through it for completeness. So we have 0 on the left in terms of charge, +1 on the right for +1 for the positive proton, -1 for the negative pion, so that cancels out. So plus and a minus becomes 0. Let's look at baryon numbers. +1 on the left, +1 on the right for the proton, and the pion has got a 0 because it's going to be +1/3 -1/3, they cancel out. And last but not least, the lepton number, 0 leptons on the left, so it's going to be a number of 0 for the lepton number on the left, and 0, 0 on the right, because both are baryons and not leptons. So question 2 is a really good question to practice your conservational laws. Okay, let's look at question 3. Which of the following rows correctly identifies particles X and Y? Okay, so particles X and Y. Well, first of all, let's look at our options. Well, we've got a proton potentially, but already it's showing us that it's going to be a down quark. So this is an example of a Feynman diagram. If you haven't looked at the lesson, as I said, I do go into Feynman diagrams. So already we've got to make sure that this is an up or a down or a quark, because a proton is not a quark. So the format is incorrect. For those of you who do know your Feynman diagrams, if this is a down, this definitely has got to be an up, and we know that the weak force has the capability of changing an up to a down and vice versa. So if you knew that already, you could have already selected D, but in this case, the up has got a positive charge +2/3, and some of that positive charge will go on to the positive positron, and then emitting an electron neutrino as well. So the answer is going to be D, so an up quark via a W plus boson via the weak force gives you a positron and an electron neutrino in the process. An up quark becomes a down quark. And then finally, what is the quark composition of an antineutron? So if you know the composition of a neutron, it should be an up and a down down, and that if you look at the charges, that's +2/3 plus a -1/3 plus another -1/3 +2 -1 -1 gives you 0. On the top, 0/3 is obviously 0, and then we put a horizontal bar on the top to represent it being an anti-baryon in this case, antimatter. So they're all anti-quarks. The correct answer is D, and not C. C would be a proton or an antiproton. Okay, so those are the first 4 questions. Let's look at the next question. So now we go on to the non-multiple choice questions. In fact, let me just go down to the bottom, because let's just finish off the multiple choice questions first. Now remember, if you looked at my lesson, there was this hexagon I got you guys to remember, or I recommended that you remember, because it's not going to be given in your data sheet in your exam. And it was the hexagon of mesons, and there were pions and there were kaons, and they showed you your respective quark composition. So if you look back into my lesson, there is that hexagon where it shows you the respective constituents of the kaons and the pions. And if you looked at that, a positive kaon is indeed an up quark and an anti-strange quark. Okay. Question 9, so just for context, or just to say, question 8 is sheer memorization. Okay, there's no way of working out, oh, how can I work out positive kaon? The only thing you definitely know from a kaon, it will have a strange quark, but that's not going to help you because all these options have got strange quarks. So you need to know the correct order. Yeah? Right, let's look at question 9. Which of the following statements about particle interactions is false? So first of all, you've got to remember that strangeness is not conserved in weak interactions, and I spoke a bit about this in the lesson that I did, where I said when a kaon, which is the heavier of the two, the pion and the kaon, when they are formed via the strong force, you get a pair of kaons being formed, where you have a positive or a strange quark and an anti-strange quark to get rid of, to cancel out the strangeness. So strangeness is conserved in strong formation, the strong force when it's forming kaons, but in decay, which is via the weak force, these heavy kaons with these strange quarks, they decay into the lighter, more stable pions with no strange quarks. So weak interactions don't conserve strangeness all the time. Okay, so let's move on now to the non-multiple choice questions. So you have an idea of the style of questions that they can ask you. So state which law of conservation is violated in interaction 1. So again, this is getting us to practice the law of conservation. Let's look at the baryon numbers. So we have baryon number of 1 on the left because it's a neutron, baryon number of 1 on the right for the proton. They're both baryons. The electron, or the positron, sorry, has got a baryon number of 0. Electron neutrino baryon number of 0. So the baryon number is conserved. Let's look at lepton number. The neutron has got a lepton number of 0 because it's a non-lepton. Proton, a lepton number of 0. The positron has got a lepton number of -1, and the electron neutrino has got a lepton number of +1. So they cancel out on the right, 0 on the left. So for last but not least, let's look at charge. So it's 0 on the left, +1 for the proton, +1 for the positron, and 0 for the electron neutrino. So it's 2 plus on the right, 0 on the left. Charge is not conserved. State and explain, this is 6.2 now, state and explain which particle in interaction 2 could be removed to give an interaction that obeys all conservation laws. Okay, well, let's first of all look at all the laws. So we have +2 from the 2 protons, 0 from the neutron on the left. We have 3 plus -1, so we have +2 charge on the right hand side. So charge appears to be conserved. Lepton number is conserved because they're all baryons. Let's look at the baryon number. So it's +1, +1, +1, +1, +1, +1, and -1. So the charge is, sorry, the baryon number, we've got less on the right hand side. It's only 2 because these guys cancel out. So in order to conserve the baryon number, and it only asks us to remove which particle should be removed, we only have got one choice. We've got to remove the neutron, because if we remove either of the protons, that would violate the charge or not conserve the charge. 6.3, state one particle that should be added to the products in interaction 3 to give an interaction that obeys all conservation laws. Explain your answer. So we start with a muon negative, and we get a negative electron, and then we have an anti-electron neutrino. Let's look at the charges first of all. So you have minus on the left, minus on the right. This is neutral, so 0 charge. Baryon numbers are going to be 0 on both sides because these are all leptons, so we don't need to worry about baryon numbers. Let's look at lepton numbers. So it's going to be a lepton number of +1 on the left, +1 for the E minus. This is an antimatter, so it's going to be -1 for the anti-electron neutrino, which would cancel out with the +1 lepton number of the E minus. So we need to introduce a a standard lepton on the right hand side, and it's got to be not too heavy. So the best option here would be a muon neutrino, which would give us that positive lepton number to balance out the lepton numbers on the left and on the right, and the muon neutrino is not too heavy. Now, if you wanted to think about the electron neutrino, the reason why the electron neutrino isn't a good answer in this case is because we've already got an anti-electron neutrino, and these guys always tend to come in pairs, the anti-electron neutrino and the electron. So that's why in this case the muon neutrino is a better answer. Okay. Right, 6.4, Explain energy must be conserved when a particle decays. Explain why it is not possible for a free proton to decay into a neutron without the input of energy. Okay, so what did I put here? I said a neutron has got a higher S energy, and if you look at your data sheet, you'll actually see that the neutron has got a higher S mass energy than the proton. So energy must be supplied to a proton in order for it to turn into a neutron. Okay, it's that idea of law of conservation of energy. Okay, so it's got that slight difference in energy, and hence why you would need that small bit of energy for the proton to become a neutron. Right, 6.5, explain why strange particles must always be created in pairs when produced via the strong interaction of the strong force. This is what I said in my lesson, that in the strong interaction when you're producing these heavy kaons, if you start off with 0, when you make a pair of these kaons, one with a positive strange particle and an anti strange particle, that +1 or the -1 and the +1 are going to cancel out. Okay, so that's why they always have to come in pairs, where the strange particles or their respective the strange particle and the anti-strange particle cancel out in terms of their strangeness. Okay, but be aware it is produced, not decay. If it was decay, then you wouldn't have this conservation of strangeness. Right, scientists believe that there is more matter in the observable universe than antimatter. Explain this. Explain why this is surprising and suggest what this may imply about particle interactions in the early universe. This is a very intriguing point because if you think about it, the law of conservation of charge, baryon number, and lepton number mean that you should always, and even actually with pair production and annihilation, there should technically be an equal amount of antimatter and standard matter. And technically we humans or the Earth or anything else in the universe should not exist, because for some weird reason we see a greater amount of normal matter, which is us, and less amount of antimatter. And that can only mean that these laws of conservation of baryon, lepton numbers, and charge to some extent were not necessarily followed in the early universe. Okay. Right, 7.1, state the name of the only stable baryon and give its quark composition. So out of the entire list, the only stable baryon is going to be the proton, because the other ones are mesons, and the neutron is obviously slightly heavier. It's got a bit more energy, so it's more stable than the the proton is more stable than the neutron. Okay, and the quark composition is going to be UUD. Okay, so another one to remember, and of course the neutron is UDD. State 3 particles on the table which do not experience the strong nuclear force. So the strong nuclear force, remember, has got a very small short range, and leptons don't experience it. So all those leptons are going to be the electron, the muon, and the neutrino from that table there. Pions are exchange particles. Explain what an exchange particle is. Okay, so these were the bosons that we talked about, and also the pions are responsible for acting out the strong force between the proton and the neutron, holding them together. So the exchange particles are the particles that are transferred between the particles when a force acts between them. Okay, so the strong force acts between them, but it is going to be the particle between them. Okay, and the force gets transferred. So 7.4, compare the properties of an electron and a positron. Positrons have the same mass and size of an electron, but of course they have a positive charge, as with any form of antimatter. The existence of the neutrino was hypothesized more than 30 years before it was detected. Explain why the existence of the neutrino was hypothesized. Again, this is to do with the law of conservation of energy. Scientists found out there was some small amount of energy missing, which they then later discovered to be these neutrinos, which accounted for that lost mass. And this equation E equals mc squared tells us that relation between mass and energy. State the type of radioactive decay that produces positrons. It's going to be beta plus decay, and this is what happens in PET scanners, which stands for positron emission tomography. Right, 1.2, write an equation showing the annihilation of a positron and an electron. So in my lesson on this, I showed you a diagram where you have antimatter interacting with some normal matter, in this case a positron and an electron, and they produce two photons moving away from one another, and I introduced that equation E equals hf, h being Planck's constant. So you have the two rest masses of the respective particles, multiply that by the speed of light squared, equals mc squared, 2 equals mc squared equals 2 equals hf. But that's the equation there. Okay, the photons produced the annihilation producing the annihilation have a frequency of 1.24 times 10 to the 8 terahertz, which is times 10 to the 12. Show that the rest energy of an electron is 8.2 times 10 to the 14. So remember, because we have that relationship 2 equals mc squared equals 2 equals hf, the 2's can cancel out. So we can do basically just work out E equals hf is going to be one of the rest energies of the electron. So it's going to be 6.63 times 10 to the minus 34, which you can find in your data sheet, which is Planck's constant, times 1.24 times 10 to the 20. We add the 12 to the 8 in the power there, because it's terahertz, because we want it all in SI units, we want it hertz, and it becomes 8.22 times 10 to the minus 14 joules, which is what the question wanted us to prove. Explain why it is not possible for one of these photons to produce an electron and a positron. So one photon does not have enough energy because each photon has only half the energy, the rest energy of the electron and positron. Okay, so again, we can't have, and in this particular case, we know that the electron, the positron are fundamental particles, so these would have to be even smaller particles, okay, if they did exist. Rubidium 8237 is often used as a radioactive tracer. Generators of this tracer contain strontium 82, which decays to produce rubidium 82 without emitting any charged particles. Describe what happens in the nucleus when strontium 82 decays to rubidium 82. So this is an electron capture process. So one proton captures an electron and it turns it into a neutron, emitting an electron neutrino in the process. So this is one of the Feynman diagrams, electron capture with a proton, which I said in the video is worth remembering. So make sure you remember that Feynman diagram. 1.6. Positrons are also produced in pair production. Explain why both positrons and electrons must be produced in pair production to conserve charge. Well, first of all, photons have got no charge, so when particles are created from them, the total charge for them has got to equal 0. So a positron with a positive charge and an electron with a negative charge, they cancel out, which makes sense why they are produced in that way. Right, kaons and pions are both types of mesons. State what is meant by a meson. So definition of a meson: mesons are particles which contain a quark and an antiquark. And remember, we have that hexagon shaped diagram which I got you to remember, giving you the compositions of the kaons and the pions. 2.2, determine the quark composition of the positive sigma baryon. So this is another example of a heavy baryon. Again, this is going to be very unstable and is likely to decay, as we can see there. Oh, actually, no, this is it being produced, but it will decay in time. So it's going to be a strange and an up composition, and the reason for it is because we've got this meson here, and that will have a strange quark. And let's look at the strangeness before the interaction. The strangeness, actually, sorry, that's a pion, sorry. So there's no strangeness before the interaction. So we've got to cancel out the strangeness after it's produced, because strangeness has got to be conserved in this particular case. Um, there is an anti-quark in the K plus. So again, if you have memorized the hexagon, you will know that there is a anti-strange quark in the K plus. So there must be a normal strange quark in the sigma baryon. And we know that the charge of the sigma positive baryon has got to be +1, and an S quark has got a charge of -1/3. So the other two quarks must therefore, in order to give a +1 charge, must be +2/3. Okay. In terms of, if you said that, well, what about top? Because you have up, down, up is positive, top, bottom, and charm and strange. It could be charm, as it could be SCC, but in this particular case, we are always going to be looking at the lighter quarks. And if you look at the composition of the proton has got up quarks, so it's more likely to be made up of up quarks than the other ones, the heavier quarks with a +2/3 charge. Point 3, we need to find out what the particle represented by Y is. Well, we know that the K plus or the kaon meson is more unstable, and I've put this hexagon for us to look at here. So the kaons have got the heavier S quarks, which are more unstable because they're more heavier. So the kaons are going to decay into pions. And let's look at the charges. Now we have got a plus charge on the left, a plus charge on the right, and a neutral charge here. So this can't be a plus charge or a minus charge, so it's got to be a neutral pion. Okay, so that's my line of reasoning there. Let's check everything else. Baryon number of 0 on the left because it's a meson. Baryon number of 0 because it's a meson. 0, 0. There are leptons. Lepton number is 0 on the left. No leptons. These guys, lepton numbers cancel out. -1, +1. Okay. 2.4. Write in an equation to show the change in quark character that happens during the decay shown in equation 1. Okay, so in this particular case, we have the anti-S quark becoming a U, anti-U, which is this one here, plus a muon, positive muon. So this is an anti-muon plus an electron, a muon neutrino. Okay, and the reason why we have said it's a U, anti-U, you could also put a D, anti-D if you wanted to, but that is one of the answers there. Okay, so it's just testing your knowledge of U. Do you understand that the anti-strange has got to go to an anti-quark as well? Okay, just to conserve the baryon number, because it will be -1/3, -1/3. Okay, so 2.5, show that the baryon number is conserved in equation 2. So we have the K plus, so we have the U, which is +1/3 plus a -1/3. So baryon number is going to be 0 at the beginning, and it becomes a pi plus. So pi plus, we have +1/3, -1/3 here, plus a pi naught, +1/3, -1/3. They're always going to be that because they're mesons. So it's going to be 0 before and after as well 0. Okay, so that's just testing your knowledge. Do you know your baryon numbers of normal quarks and antiquarks? 2.6, state and explain which interaction is responsible for the decay shown in equation 2. So this is going to be the weak interaction, and remember, strangeness does not have to be conserved because we are going from a heavy kaon, unstable, with a heavy strange quark or anti-strange quark, and that decays into a lighter, more stable pion with no strange quark. Okay. So we have complete table 1 to show that the daughter nucleus and one of the particles emitted, we've got to fill in these numbers here, or these blanks. So we start off with K40, 19, and that decays into by emitting beta minus. So we've got to put a 0 and a -1 here. The daughter nucleus will have to be 1 greater than the 19 in order for the sums to add up. And this is the same idea back in GCSE with these type of equations. 40 equals 40 plus 0, 19 equals 20, take away 1. Okay, so that's your line of reasoning. So the daughter nucleus will basically have one of the neutrons being converted into a proton, hence why the atomic number goes up by 1. 1.2, if beta minus decay only produced a daughter nucleus and a beta particle, it would violate the conservation of lepton number. State the particle which is also emitted in beta minus decay. So beta minus decay will always have a corresponding anti-electron neutrino decay. This is just one of the things you've got to remember. Vice versa, if it's a beta plus decay, you're going to have an electron neutrino being emitted as well. Okay, so there's always going to be standard lepton and an anti-lepton being emitted in the form of a neutrino and vice versa. Okay. 1.3, describe what happens to the quarks in a neutron when a beta minus decay occurs. So a down quark is going to change into an up quark by the weak interaction. So this was one of the Feynman diagrams I showed you in the lesson. Okay, so make sure you remember the Feynman diagram for the beta minus and the beta plus decay. The exchange particle in a beta minus decay is the W minus boson. Compare the properties of this particle to those of the exchange particle used in an electromagnetic interactions. So the exchange particle in the EM, electromagnetic interactions, the virtual photon. We have got no evidence for photons to have mass, apart, as I said, from the Higgs boson, which was what I mentioned in my lesson on particle physics, which gives some mass to these bosons, which would otherwise have no mass. But virtual photons are uncharged as well, whereas the W minus boson's got a negative charge, and I talked about them being massless. Okay, so those are your differences, and that's how you get your 3 marks, by also saying that the bosons have got a large mass. State the daughter nucleus that is produced when K4090 undergoes beta plus decay to form argon. So we're doing the opposite now. So if we've got 19 on the left, so first of all, let's do the top numbers. 40 equals 40 plus 0. So that's going to be the same, but we're just changing this to a plus 1. So therefore, 19 to start off with has got to equal some number plus 1 has got to equal 19. So 18 plus 1 gives you 19, hence why it's going to be that. Okay. 1.6, draw a diagram to show the particle interaction in a beta plus decay, and there you go. This is one of the ones you've got to remember. So it could be a beta plus decay or beta minus decay. Again, watch the video on my lesson on particle physics. Make sure you remember those Feynman diagrams. So look at the next one. State what happens to the positron particle produced in equation 1 when it interacts with a nearby electron, including which particles are produced. So the positron particle, when it interacts with an electron, this is basically annihilation, and 2 photons will be produced. Hopefully that's helpful. Any errors or any comments, please put in the comment section, and hopefully I'll be able to answer your questions. All the best in your exams.